So far we have discussed about DSBSC and amplitude modulation. So these are two versions of amplitude modulation that we have discussed in the previous few classes. So DSBSC was something where it's called double sideband, but also suppressed carrier. That means you modulate it the way we modulate, it's just frequency shifting actually. So you multiply the message signal by a cos omega ct, where omega c is the frequency of the carrier. Okay. So if you just do that, then you get double sideband. But if you on top of that, if you add carrier to it, then you get amplitude modulation. So the DSBSC, if I just write phi DSBSCT, that should be, if my message signal or modulating signal is mt and carrier is cos omega ct. So this is DSBSC, and amplitude modulation is nothing but the same thing, which is mt cos omega ct plus a cos omega ct. So that's the carrier part we add to the signal, and we have seen the benefit, relative benefit of it. So here in AM we have seen the receiver becomes very simple. It's just envelope detector, whichever way you do that. We have already discussed two methods of envelope detection, and for DSBSC we need we need to generate local carrier. So for that we need to extract carrier from the incoming signal. So that requires carrier synchronization and all those things. So demodulation of DSBSC was very simple. You have to again remultiply with cos omega ct followed by a band pass, low pass filter. So this is something we have already discussed. Now let us try to see, it's just some more discussion about this. You will be mostly seeing that there is a importance of tone modulation, because through tone modulation we try to get information about what happens whenever we modulate. So tone modulation means it's just it's not a message actually, it is a sinusoidal I want to modulate. So my modulating signal, that mt, I have a specific representation. So far we are not representing it. Okay. So we are just saying it's some kind of signal, maybe voice signal or something. So here in tone modulation, so we call it tone modulation, it's just indicating modulation. Actual modulation will never be that, because modulating signal we have already discussed that must have some randomness in it. If we just say it's just cos omega mt, it is not carrying any information. But this is just to say how the modulated signal will look like, what should be the frequency spectrum of it and all those things. So if I have mt equal to cos omega mt, so therefore phi DSB SCT, which is the modulated one, must be mt into cos omega ct, which is nothing but cos omega mt into cos omega ct. So I take half into 2. So this I can put as cos a plus cos b, sorry, cos a into cos b formula. So I can just put that as of course our assumption is carrier frequency is much higher than for modulation, that has to be there. So it should be omega c minus omega m. So if you just try to see in the spectrum what is happening, our modulating signal, that was sinusoidal or a cos. We have already said that cos in the frequency domain can be represented as 2 delta function, right. So if I just put this as mf, so this is at omega m, this is at minus omega m. So whenever we modulate, what happens, there are 2 cos now, one is cos omega c plus omega m. So if this is omega c, there should be one cos function which is at omega c plus omega m, and there should be another cosinusoidal which is at omega c minus omega m, and of course the negative half should have the symmetric part. So if this is minus omega c, so there should be 2 part over here with amplitude half, right. So all this must have a half amplitude. So that's phi DSB SCF. So, whenever we modulate, actually if a tone we modulate with a carrier, we just get 2 cosinusoidal, and the corresponding time domain representation will be something like this. So, this is your modulating signal with frequency omega m, and let us say that is the carrier which is having a frequency much higher. So, whenever you modulate, what we see, that becomes the, means that should represent the envelope. So, it should be something like this, and the envelope must have similar representation in the positive and negative half, and inside with omega c frequency it should, and there should be a phase reversal. We have discussed about that also. Everywhere, wherever there is a voltage, means whenever it crosses 0, there should be a phase reversal. So, that should be the time domain representation. So, if you just try to see what this is actually 2 cosinusoidal beating with each other, okay, addition of 2 cosinusoidal signal with frequency omega c plus omega m and omega c minus omega m. Once you do that, if you just take these 2 cosinusoidal signal and then add them together, you will see that this pattern will be generated. Okay. So, that is what is happening over here. So, this is how DSB-SC should look like. Whenever we add carrier to it, what happens? So, in the frequency domain, if we try to employ, so phi am t, that is of course cos omega m t, because that is the modulating one, that must be multiplied by cos omega c t, plus there should be a cos omega c t, right, a carrier term should be there. So, therefore, this part we have already means said what should be the frequency domain, corresponding frequency domain representation. So, that should be 2 cosinusoidal, this should be omega c. So, this must be omega c plus omega m, and this must be omega c minus omega m, and due to the presence of carrier, there must be a by 2 strength carrier at omega c. So, it is just, we can see that whenever we have with carrier, there should be a delta function which is just representing this carrier at omega c and minus omega c, of course, because it must be even symmetric. Okay. So, if I have just general modulated signal of this MF, so that is the MT has a Fourier transform of MF, let us say. So, if I modulate that with omega c, that should be my representation if I do DSB-SC. If I add carrier, there should be just a delta function at omega c, okay, of strength a by 2, of course. Fine. So, this is what we have means told, and this is just a tone modulation version of that. So, now what we wish to do is, we wish to see that the same modulation technique can we employ for other things. One is called the frequency mixer, or converter. Let us first try to understand the utility of that. So, generally what will be happening, suppose I wish to put some signal at a higher frequency. Okay. So, the higher frequency, at that higher frequency, let us say the available frequency, because I need to get a frequency slot which is in the media nobody is occupying. Okay. So, that might be very high, pretty high. So, what I need to do while putting, I need to modulate with that omega c, but in between I might have to do some signal processing, like I might have to amplify the signal and so on, some other signal processing I might have to employ. Okay. So, if I wish to do that, what I can do is something like this. I can first modulate the signal, or even demodulation also similar thing will be happening. So, I can put it into a intermediate frequency. let us call it omega if. Similarly, in the negative half also same thing will be happening, and then after that from omega if will be actually translating it towards omega c, or sometimes I might do the reverse thing, that after receiving whatever signal I receive. So, suppose my modulated signal is coming. So, this is centered around omega c minus omega c. I put a band pass filter centered around omega c, and the bandwidth should be greater than the 2b value, right. We have discussed about the bandwidth for a modulated signal. Okay, so, I will get just this one. If there are some spurious thing in other frequencies, that will be all means rejected. I will just get my signal. Now, once I get this signal, I might have to amplify this signal. Okay, so, the received signal has to be amplified, but at that high frequency, if I wish to put amplifier circuit at high frequency, any circuit design will be very difficult, because they will all start radiating things. Okay, so, any circuit component you start putting, they will be all radiating. So, I cannot really employ any signal processing at that high frequency. So, what I wish to do, I still need to do amplification and any other signal processing that I wish to do. So, I need to first translate it to a frequency band where I can do my signal processing. See, the good advantage is while modulating and transmitting the signal, I am still using omega c, which is a requirement in the carrier, or sorry, requirement in the channel, because I need to put a signal in that particular frequency band, that is the only free frequency band. But I also know at the same time that processing I will not be able to do at that frequency. So, I have to first receive that. So, receiving is still all right, I can put a band pass filter at that frequency centered around omega c with 2b bandwidth, I can take that signal. Now, with a very simple circuit, if I can just down convert it to a lower frequency, then I can employ all my signal processing things on that. So, all I have to do is, if I get this signal, let us say centered around omega c and minus omega c, that is my received signal. I wish to at that frequency level, now I have rejected after band pass filtering, I have rejected all other things. Now, I cannot do signal processing over there, I want to actually translate it back to omega if, which is pretty low frequency where I can do signal processing. So, all I have to do is from this to this, I have to do a conversion, okay, which means, see, the spectrum or the signal frequency components remains the same, it is just getting translated into one frequency to another frequency. So, all we have to do is, if the modulated signal was mt cos omega c t, from there I will have to create mt cos omega if t, this is all that I will have to create. Okay. So, that is something we will have to create. Now, this is something which can be done almost equivalently with a similar modulation technique. So, what I can do, suppose this is something I am receiving. Okay. So, this whatever I am receiving cos omega c t, I will actually multiply this with 2, I am just taking means you will see that why I am taking 2, but I just have to multiply it with something called cos omega c plus omega if t. Okay. So, this is all that I will have to do. So, I have to locally generate a particular sinusoidal which is centered at omega c plus omega if, or I can do it even at minus, both will give me same result. Okay. So, I just have to do that and I have to multiply it. So, my circuit will look like this. This is mt cos omega c t which is coming to me, I receive it through an antenna, then I put a multiplier circuit, whichever way we have already talked about how to design a multiplier circuit, and then I multiply this with cos omega c minus or plus omega if t. Okay. Whatever I do get, after that I put a band pass filter, okay, which is centered around that omega if. You will say that this will give me this particular signal back. Why? Let us try to manipulate this particular part. So, I am just doing multiplication. So, after multiplication I will get, because it is 2 cos into cos a cos b. So, I can put cos a plus b plus cos a minus b. So, cos a plus b, suppose I am just taking the positive sign. So, that should be 2 omega c plus omega if into t plus cos, and this minus this, so that should be just omega if t, right, which is my target. Now this is at omega if, this is at very high frequency, twice of omega c plus omega if, right. So if I just put a band pass filter around omega if, okay, which is having a bandwidth of 2b, so what will happen, this whenever I see this will be creating something at omega if, and it will be creating something at very far, which is 2 omega c plus omega if, right. So that is what I will be getting. Now if I just put a band pass filter, I am just showing the positive spectrum, similar things will be there in the negative half also. So if I just put a band pass filter, this will be rejected. So immediately what do I get? I get this mt, so this term will be cancelled, the leftover will be cos omega if t, which is my desired signal, right. So this particular methodology is called as either frequency mixer or frequency converter, because what we are doing, we are not changing the message signal, we are just translating the carrier from a higher frequency to a desired lower frequency, which can be done. Here also you might be asking that I have to generate a local carrier, does that need to be synchronized with the input carrier? Because this is at a separate frequency, we do not need any synchronization, okay. So that is the advantage of it, whereas when you are doing coherent demodulation, in that, or we should say multiplier demodulation, that means you again multiply with cos omega ct. At that point also we are putting, we are multiplying with it and we are putting a low pass filter, but there the frequencies has to be completely synchronized. We have talked about that, that if this is cos omega ct, that has to be cos omega ct. Here neither the frequencies are synchronized, so it must be some other frequency, so I can always generate it, and will later on prove also the phase also need not to be synchronized with it, okay. So we'll prove that when we'll talk about that carrier synchronization and carrier recovery, okay. But right now we can just give this information that we, for this frequency converter, we do not need additional requirement of synchronization, no synchronization is required. I can just multiply with any local carrier that I generate, I need to just roughly know what is the omega c, okay. So it needs to be closer to that, and then I need to generate something at omega c plus or minus omega if. As long as I am doing that, that should be fine. So I will be able to do this. So this is a very important tool in communication again, because this frequency converter, as I have already pointed out, it might be required in many cases where you might have to modulate at a very high frequency and you might have to translate that down to a desired frequency band where you can do signal processing, which might be a big requirement. So that is one technique you can already see that which can be employed for communication, but it is actually not affecting what you are doing in the channel. In channel you are still choosing that omega c, right. So that is one thing we have talked about. The other thing we wanted to talk about is actually the relative advantage or disadvantage due to this amplitude modulation, okay. So advantage we have already talked about, that the receiver side is very simple, right. We just need to do a envelope tracker or envelope detection, which is a very simple circuit. We have already talked about that, that you need a just a diode and then followed by a low pass filter, okay, either low pass filter or a RC charging and discharging circuitry with properly designed R and C. We have already talked about that. So it might become very simple, you do not need any carrier synchronization, you do not have to generate carrier yourself, so all those things are not required. Whereas if you wish to do without carrier, that means not amplitude modulation, that DSB-SC, where carrier is suppressed, you might have to locally generate a carrier which is synchronized with the incoming carrier, or you might have to actually take the carrier, means extract the carrier from the incoming signal and then demodulate it, that means you have to multiply. So let us try to see, it might be advantageous, okay, in that aspect. Let us try to see if there is any disadvantage, because there are no free lunches. If we try to get some advantage, there must be some disadvantage. So let us try to see what the disadvantage we get. So whenever we add a carrier, what was our purpose? This is also something we have discussed, that whenever we add a carrier, the message signal, whatever way it was, the lowest amplitude, whenever we add carrier, it is actually almost like adding DC value to the message signal and then doing DSBSC, right. So, the DC value, which is actually the amplitude of the carrier, that must be greater than the lowest amplitude of the message signal. This is something we have already proven, that my MT cos omega CT, I add A cos omega CT to it, which actually this is the phi or phi AMT. So, this is, we can just say MT plus A into cos omega CT. So, this is my new message signal, where with MT I am adding A, and if I wish to do envelope detection still, we have seen that it must not have any zero crossing, because whenever I have zero crossing, I will have that phase 180 phase shifting, and then I won't be, my envelope tracker will not give me the signal back. So, even if I add a DC to it and it still has some spurious part which is below, means 0 level. So, if I just try to see the envelope, it will have this thing, and then the carrier will run on top of this, and there will be a phase reversal. And if I wish to do envelope detection, so envelope will detect this, this and this. So, my detected signal will look like this, which is not the original replica of this one, right. So, whatever I need to do, I need to take this up. So, carrier must be added in such a way that the amplitude of the carrier is always, means whenever I add that, amplitude of the carrier is always greater than even the lowest value of my message signal. Okay. So, let us say that lowest value is minus MP. Okay. So, therefore, I have a condition that A must be greater than this MP. Okay. This must happen, and in that aspect we define a term called modulation index, which is defined as mu, which is actually MP divided by A, where MP is the lowest value of my message signal. Okay. Or you can write that as M min, whichever is good for you. But anyway, this is the modulation index that has been defined. So, if you just see this definition, immediately you can see that mu must be, of course, greater than 0. Okay, because if it is less than 0, then A will be negative with respect to MP, right. MP is already a positive, because minus of MP is the negative value. So, MP will be always positive, it is the modulus value of that, and then if mu is negative, then A will be negative, which is not good. Okay. So, all we will have to do is that mu must be, that is a trivial one, it must be greater than 0 always. But the other one is very important, because A must be greater than this. So, immediately from here I can write MP divided by A, that must be less than 1. I just took A down. So, MP by A must be less than 1. So, I can also write this. At max I can have equality, but anything other than equality I put, always I will have the danger of this kind of scenario. Okay. So, I should be, this modulation index, I should be always ensuring that this is happening. Okay. Now, let us try to see what is the effect of this. Okay. So, let us say I have some, let us say I put a phi AMT, which is nothing but some A cos omega CT, that is the carrier part, and I have some message signal into cos omega CT, right. Now, this is the carrier part, and this is that DSBSC part. Okay. So, what is the power of this one? So, I am trying to calculate the power of this one. So, I know it is a cosinusoidal, so it should be A square divided by 2, if you just evaluate the power of that. So, this is P carrier, PC I call it. And what is the power of P signal? Suppose MT has a power PS, that is something I know already. The message signal has a power of PS. Now, if I multiply with cos omega CT, we know that the power becomes half. We have already discussed that in the previous class. So, this must be PS by 2, that is the power of this part. Okay. Fine. So, this is my 2 power. So, I call this P signal. Okay. Now, let us say talk about some efficiency. Okay. Ultimately, what I am trying to do, I am trying to actually transmit MT through the channel. Okay. So, the significant amount of power which is actually required, or which is the valuable power, that is actually this PS, right, the signal power. So, that is the power I wish I could have transmitted. If I was not employing any carrier modulation, I could have in the baseband I could have transmitted this. So, MT was getting transmitted. So, corresponding signal power was PS. So, this is the one I will be wishing to transmit, whereas due to this particular modulation I am transmitting little bit more. So, what is the thing I am transmitting? So, I should have transmitted PS, but right now I am transmitting what? I am transmitting this A square by 2 plus PS by 2. Okay. If I compare it with DSBSC, in DSBSC I will be transmitting only this. So, how much I will be transmitting? PS by 2. So, that I would have eventually transmitted if I was transmitting DSBSC. Now, because of this particular thing, I have to transmit power for this as well as power for this. So, this is the overall power I am transmitting, right. So, immediately I get, so that is the efficiency to actually which I could have done with PS. Now, I am transmitting A square plus PS. So, that is the overall power efficiency that I get doing this, right. So, I am transmitting extra amount of power which is A square. So, this is always sitting inside. Okay. Now, let us try to see with this efficiency factor. So, better the efficiency, I am better off. If I just transmit DSBSC, then below also I will not be transmitting this A square. So, it will be 100% efficient. That means, whatever power I have to transmit, I am just transmitting that much. But if I do AM, then probably I am transmitting little extra power. That means I am wasting that power, because for transmitting carrier I am getting no advantage. That is not carrying my signal, right. So, what I can write, suppose if I have a tone modulation, right. So, my MT is something called A cos omega MT, and I have a modulation index of mu that is added to it. Okay. Because if I just write it as some AS cos omega MT, okay. So, what is the lowest value of that? It is minus AS. Okay. What is the PM for this, which I was talking about, the lowest value of this? That must be AS. Okay. So, I should have my carrier signal AC. So, that means AS divided by AC must be my modulation index. Okay. So, therefore, I can write AS as my mu, whatever modulation index I am employing, into AC. So, or A, if I just put this as A. So, mu into A, so I can write this, right. So, that is my MT, okay, or MT cos omega CT if I just write, okay. Then this should be multiplied by cos omega CT, right. So, my overall signal is A cos omega CT plus mu A cos omega MT into cos omega CT. So, this is what I am, again we are demonstrating a tone modulation, right. So, in this case, for the message signal, which is this part, what is the power of it? It is mu square A square, right. So, that is the power divided by 2, that is the power of the message signal. So, this I can call as PS, and immediately I can evaluate the efficiency, which is mu square A square by 2, right, divided by A square plus mu square A square by 2 according to that formula. That is PS divided by PA, or A square plus again PS, right. So, this is what I get, A I can cancel out. So, I get mu square divided by 2 plus mu square, right. If I just put mu equal to 1, that is the best I can do, that is the highest modulation. If mu equal to 1, I will be seeing almost this, the envelope just touches, okay, it does not cross over. Anything bigger than that will be below this. So, if I just put mu equal to 1, immediately what kind of efficiency I get? If you put mu equal to 1, it will be 1/3, so 33% efficiency. So, that is the best I can get. So, immediately you can see that is where I pay. DSBSC, whatever power efficiency I was getting, compared to that in AM I am getting 33% efficiency only. So, that means 1/3 power is the useful power, rest of the things are just wasted. Okay. So, we will end it over here for this class. Next class we will start defining other bandwidth efficient modulation.